We were talking about limits. Section 1.2 we didn't quite finish. So let me give you some quick review problems here, just to get us thinking along the right lines again. So if I asked you to find the limit and I give you something like the limit as x goes to 2 of, oh, let's say x cubed, what are you going to tell me? What is it? 8. Why?
Plug it in.
You can just plug it in. Right? There's no problem here. Right? So if you plug the 2 into the x, you'll get 2 cubed, which is 8. So this limit is just. What if I give you, let's see, what else did we talk about? What about if I give you this? Limit as x goes to 0 of absolute value x.
Yeah.
0.
That's 0.
0, why?
Just plug it in and 0 is positive.
Again, there's no problem. Think of the graph. The way limits work. Okay. If your graph doesn't jump or break or have any problem, then you can just plug the number in. So the way absolute value of x looks, it's a v. Okay? And as x goes to 0, so as your x values are getting closer and closer to 0, you want to know what happens on the function. Where are the y values going? The y values are going to 0. Or another way is, well, you can just plug it in. There's no problem. Let's see. Here's one I didn't get to last time, but it's kind of tricky, so I want to talk about it. What if I gave you something like the limit as x goes to 0 of absolute value of x over x? Some people say 0, some people say does not exist.
0.
Okay, so if you plug 0 in, you got a problem, right? That's one thing to notice. If you put 0, you'll get 0 on top, 0 on bottom, that's undefined. Okay? But that doesn't mean the limit doesn't exist necessarily.
Because we're not actually having 0 in the bottom, we're just as it gets close to 0. And since I have 0 on the top, so it's going to equal 0.
It would be -1 and 1. It would jump.
Right, so a little bit further analysis is needed than just plugging it in here. You really have to know what the graph looks like or what some points look like at least. Yeah, yeah. What does this graph look like?
Either a line or a line with a v at the origin.
It jumps at -1 and 1.
Two different lines.
So plug in, for example, a positive number here. Right? If you plug in 1, let's do 2, absolute value of 2 over 2 is 1, right? And that's going to happen no matter what positive number you plug in.
0, 0.
So for any positive x value, this is going to be 1. At 0, it's not defined because you get division by 0, so I'll put a hole. What happens with negative x values?
They are all negative.
So yeah, as soon as you put in a negative x value, if you make it -2 absolute value over -2, this will go away and become positive, but this one will stay negative. So it's -1. No matter which negative number you plug in, you're going to get out -1. So as you approach 0 on the x, what's happening on the y values? They're either going to 1 or negative 1. Up here on the graph, if you're approaching x equals 0 from the right side, you're going to y equals 1. And if you're approaching from the left side, you're going to y equals negative 1. So what's your overall answer for this limit?
Does not exist.
Does not exist. This limit does not exist. What if I gave you instead the limit as x goes to 100 of absolute value x over x?
1.
That's 1. Right? Because at the x value of 100, there's no problem. At the x value of 100, you're up at 1. What about the limit as x goes to 2 of absolute value x minus 2 over x minus 2?
That is also
Why is that?
because it makes it 0 at and 0 at the bottom.
Well, the fact that it makes it 0 on bottom and 0 on top is not enough to say it does not exist. That's not enough logic, right? I mean, there are plenty of functions, for example, limit as x goes to 0 of x squared plus 2x over x. This is 0 on top and 0 on bottom, but this limit does exist.
It'd be 1 at
They
least.
approach different numbers.
Now, this guy is a problem because he's essentially this again.
Yeah.
Right? I've just taken this x and replaced it with x minus 2.
The retranslation.
Yeah, it's the same exact graph, just shifted 2 to the right. So the limit as you go to 2 is not going to exist again. For a similar reason as up here. What's this limit since I wrote it up here?
X plus 2.
You can simplify this, right?
Maybe 2?
Yeah, if you factor out an x, you're left with x plus 2 on the top. So those x's cancel. That means there's a hole in the graph. So this function here that I'm trying to find the limit of has a hole at x equals 0. Otherwise, it looks like x plus 2. So if I were going to graph this function here, I would graph x plus 2 with a hole when x equals 0. So this limit will exist because as x goes to 0, we are approaching a single finite y value. We're approaching the y value of 2. It's not on the graph, but we don't care. We're still approaching. So just because you have 0 on top and 0 on bottom doesn't mean the limit does not exist. You have to have a little bit more analysis. You have to show or somehow reason out that you're not going to a single y value, a single finite value. In fact, let me give you a similar example to this one here. I'm going to write 3 functions for you. So I'm going to give you f of x equals x squared, g of x equals x squared if x is not equal to -1, and 100 if x equals -1. And I'm going to give you h of x equals x squared times x plus 1 over x plus 1. Now I want you to answer basically 6 different questions for me. So I want to find the limit as x goes to -1 of f of x. And I also want to know what f of -1 is. And then we'll do it for each of the functions. So let's talk about f of -1 first, because that's pretty straightforward. For this function f of x, if you want to know f of -1, you just plug in -1, not a problem. Right? So what's f of -1? 1. You just plug it in. 1 squared. -1 squared. What's the limit as x goes to -1? It's 1 again. 1. There's no problem. You can plug it in. It's not going to different values. It's just a parabola. Right? It's just a u. There's no jump. There's no break. There's nothing funny that's making you approach different y values. So if you plug in -1, that'll give you your limit of 1. So this is the best case, when you can plug in the number or do the limit and you get the same result. Okay? In fact, this is what makes a function continuous. When these are the same answer, your function is continuous at x equals -1. We can talk about that more in a later section. But for now, it's really nice to just be able to plug in the number. Okay, but what happens with g here? If I do the limit as x goes to -1 of g of x versus g of -1, what happens?
It's 100.
G of -1 is pretty easy to calculate, right? What's that?
Doesn't exist.
No, g of -1 exists. Yeah, so g of -1 would mean you go into this branch of the piecewise function and you get out 100. But what about the limit as x goes to -1 of g?
10.
100? What's the graph of g of x look like?
A line with a hole and a point.
Not a line. Not a line, right? Because g of
A
x
parabola with a
is...
hole
Yeah.
and a point.
Yeah, because g of x is usually x squared. For almost all x values, right? For every x value that's not -1, g of x looks like x squared. So for g of x, you're going to look like x squared, except at -1.
20 times 100.
I'm saying take out that guy and at -1 put in 100, so way up here somewhere. So this extra point that I placed in manually is why g of -1 equals 100. But the limit doesn't care about that single point. The limit cares about the trend. The limit cares about what's going on all around x equals -1. So if you look at the trend as x approaches -1, on your graph you're going to approach the hole, which has a y value of 1.
Oh.
This guy is over here. Right, that hole is the same, is going to be at this location. You can figure out where the hole is by plugging, where the y value of the hole is by plugging in -1 here. So, for h, what's the difference? What's new here? What does the graph of h look like?
That with the hole without the point.
Yeah, it's similar to all of them, right? Because they all have the basic shape of a parabola. But this x plus 1 factor I put in top and bottom does what? Makes a hole. Because it cancels, it makes a hole at
-1.
x equals -1. But it doesn't get filled in. Right? I haven't in any way indicated that the hole should be filled in here. So for this graph,
It's basically that one.
it's basically this one without the point. So we had an x squared, but we took a point out. So for this part, h of negative 1, undefined, because there's no, when x is negative 1, there's no y value. So this is undefined. What about this? 1. 1 again. Right? Because the trend's the same in all of these cases. Whether this point is here or not there, or you've replaced it with a different point, doesn't matter. Right? Your y values are still approaching the same thing, 1. So kind of the overarching issue or the idea here, if you have a function that's the same everywhere except at one point, the limit will always be the same at that x value. So sometimes you'll see these piecewise functions, okay? And if your piecewise function has just one single point taken out of it, then as far as the limit goes, you only focus on this. And this point doesn't affect the limit at all. Give you something. Oh, here, I guess. Let's do the limit. The limit as x goes to 0 of e to the 1 plus x minus e over x. You guys know about e. I didn't hear you, sorry. It's an exponential function, right? It's approximately equal to 2.72. Okay. So e, the number e, without any exponent on it, is a transcendental number, like pi. It's a decimal, it goes on forever. Okay? It's approximately equal to 2.718 or 2.7. It's a special number for lots of reasons that we won't get to until chapter 5, but you have to trust me for that. How would you evaluate this limit, though? What's happening here?
Is that an x or a 2? E1 plus...
There's no 2's in here anyway.
1 plus x.
Is that
This one here?
Yeah. Okay.
Is that a 1 or
Wouldn't it be approaching 0?
This is 2.718. Say it again?
0?
You guys think this approaches 0?
Yeah.
Certainly, when you plug 0 in on the bottom, you get 0, which is bad. When you plug 0 in on the top, what do you get? E minus E, so 0 again. So hopefully you're seeing that when you get 0 over 0, you need some sort of more analysis. You can't say.
Yeah, if you put in something like really small.
Right, so yeah, the idea here is going to be make a table. There's really no other method to approach this. I don't know what the graph of this looks like, okay? Because it's a fraction with an e to the x in top. I couldn't graph this if I tried right now. Well, I probably could with my table. It would be difficult. So I don't know what the graph looks like. I can't plug it in. Really, my only other method is to make a table. So you would do something like x and then y, or I guess this guy. And then because you're trying to find the limit as x goes to 0, you want to center everything around 0. So at 0, this is undefined. But But then you could plug in something like 0.001 negative. Negative 0.01, negative 0.1. Remember this? And just see what happens. So I might pull it up there in a second, but I have these values, let me write them down for you. So you should get 2.5868 here, 2.7047, 2.7196. Oops, sorry. 69. This one's 2.7196. 2.7319. 2.858. So my question is kind of what do you think this approach is?
2.7,
E.
1.
Approach is E.
Oh.
Right, so I picked this because this is a really difficult limit to evaluate. Okay? And even with the table method, it leaves something to be desired because you can't see this is going to E exactly. You can guess it's going to E because E is about 2.718, and this is 2.717, and this is 2.719. You can guess it's going to E, but we don't really have enough technology yet to show that this is going to E. So, but it is. We'll do that in chapter.
Is it like a general rule?
This is actually, believe it or not, this is saying that the slope of the tangent line of E at 1 is E. So let me, real quick, just so you kind of have a background on why we're going to care about E. Remember, I spent all this time, last time, talking about the tangent line problem. For exponential functions, the general shape of an exponential function is this. Any b to the x, right? Any number to the x power swoops up like this. Okay? And depending on the base, like maybe this is e to the x, but then 3 to the x, a higher base, would swoop more steeply. So maybe that's 3 to the x. And 2 to the x, a lower base, right? 2 is less than e. 2 to the x would swoop a little bit more shallowly. The special thing about e to the x, the special thing about this number, is e to the x is the only exponential function that has a slope 1 right here when it hits the y-axis. Okay, so exponential functions are all basically the same shape. Okay, the e is the specific one that has slope 1 when it hits the y-axis. This 3 to the x is going to have a slope a little more than 1, and 2 to the x is going to have a slope a little less than 1. Because e has this nice slope at the y-axis, it's really useful in the tangent line problem in calculus. It makes things really easy. This guy here is actually saying that if you go to x equals 1, if you go to the point 1e, the slope of the tangent line is b. But that's kind of, I guess, a prelude. For now, all I really want you to understand is that e is about 2.718. Okay, that will come in handy. And sometimes the table method is not going to be able to give you the right answer, okay? Because it goes to just an irrational number, and you'll never be able to guess what that irrational. I have one more example from this section, but let me stop for a second and take the question. Yes?
I'm sorry, could we go back to
Sure.
H?
Yeah.
understand why it didn't approach 1.
Well, it does approach 1, but that's this one.
Yeah, why doesn't that one
Because this has nothing to do with approaching.
approach? Okay,
This is actually what the point really is.
which is -1.
No, which is nothing. There's no point there. There's no y value, because there's no point.
Okay.
So, like this one was 100 because at -1, that's where the point is.
Okay.
But here at -1, there is no point, so you can't.
Okay.
You have to actually have a point to be able to answer this, and we don't have.
Oh, because they cancel out.
The top where they cancel out.
Yes, there's no point there because the x plus 1 canceled out. Yes, that's why there's no point. Right, if I would have put x plus 2 over x plus 2, then there'd be no point at -2. Over here at -2, there'd be no. So whatever makes the denominator 0 is where your hole is for these. If the factor cancels. Let me give you one more example and we'll go on. So here's a function. I'll draw you a function. 1, 2. It's going to have an asymptote here. It's going to have a hole at 0, 2. And it's going to go up and approach the asymptote. Go down this way. We'll have a hole at 4, 1. And we'll jump up. This guy. So there's your function. And this is f of x. So I just made this up. But I have a bunch of questions, right? This is a typical kind of problem to help see if you understand limits. So I make up a function and I ask you a bunch of questions about limits. So let's do the limit as x goes to 0 of f of x. What do you think?
2, 3.
2, right? 2. As x goes to 0, your function is going this way, and your y values are zeroing in on 2, right? Your y values are approaching 2. Does that make sense? What about f of 0? Undefined. F of 0 is undefined. Why?
A hole.
There's nothing there. I didn't fill in the hole. Right? If I go to 0 on my x, and I look up at my graph, there's no point there, so it's undefined. Or does not exist, or something to that effect. Okay. What about, let's see, what else do I want to pick on? 3. Well, let's do, yeah, we can do 3. So limit as x goes to 3 of f of x.
0. 0.
That one's 0.
Oh, man.
What are you looking at? 2?
I'm looking at 4.
Oh, okay. Yeah, so 1, 2, 3. So the limit as x goes to 3, well, my function's going. That'll make it easier. So as x goes to 3, my functions of my y values are approaching the axis, so my y values are actually approaching 0. What about f of 3? That one is 0, right? Because there's a point there. What about 4? Limit as x goes to 4. That one doesn't exist. Why not?
Because they're not going towards the same.
They're not approaching the same thing. They're not approaching a single y value. On the left of 4, your graph is going up to y value of 1, but on the right of 4, your graph is going to a y value of 2. So the limit cannot exist because you're not approaching a single y. What about f of 4?
2.
That's okay, right? F of 4 is okay. You go to 4 and you look where the point is. The point is at 2.
I have a question.
Yes?
If it would have on the C, if it would have specified the domain for infinity or negative infinity force, then we can pick. But when it's without, like, it doesn't specify certain domain is when it doesn't exist, right? Let's say if it says for infinity, then I can pick 2.
Well, but, yeah, but this is the limit of f. F is this function. So the domain is specified by this graph. The domain is everything around, the domain is 4 to infinity and 4 back to 2. So for this particular type of problem, that isn't going to work. If I erased a part of it, then you could do that. Or if I gave you like y, f equals whatever, like root x, and I said that I want to use the domain. Now I want to use this domain or something. Then I guess it's okay.
I get you.
But yeah, in general, this isn't the way we're going to do that. We can do that, but this isn't the way we'll say it. If you want to specify one side, there's a different type of limit called a one-sided limit. So if you want to specify just the right side, we're going to learn this in 1.4, you can put a little plus up here. And that means just what happens on the right of 4. So we can do that, but we usually don't do it with domain. So 5, what happens at 5? For the limit.
2.
Yeah, so limit's not a problem because on both sides you're approaching the same value. Right? No matter what, your y is approaching 2 on both sides of 5, so this is 2. And then what about the f of 5?
5.
Then you go up to the point. You go to 5 and you say, I don't care what it's approaching, I want to know the specific point. Looks like 1, 2, 3. And then the last one, I guess, that's interesting. What about the limit as x goes to 2? Yeah, so as x is going to 2, right, you're looking at x values around 2 from the left and the right. On one side, you're going up forever. On the other side, you're going down forever. These are never going to converge on a single y value. So the limit does not exist. F of 2, f of 2 is not even in the domain. What should f of 2, what should you say? Undefined or does not exist, right? Somehow you need to indicate that it's not part of the domain of the function. Asymptote. your tools for section 1.2, pretty much you have tables, you have graphs, or you can just plug things in, right? So if you want to evaluate a specific limit, you would try to plug in the number first. If that doesn't work, I would probably go to a graph. If it's an easy function, a graph, you can go to a graph, and otherwise make a table. That's kind of what we do. Anything I can clear up about what we've covered so far?